So section A.1 is called radicals and rational exponents. Since we are talking about exponents, it's important to remind you that a radical, it really is just an exponent. It's just a way of writing a fractional exponent. And since radicals are fraction exponents, properties of radicals happen to be extremely similar to properties of exponents. Well, that's not a coincidence. Like I said, a radical is technically an exponent. It's just a different way of writing it. So they have to follow the same rules. Here, if you multiply two things that have the same radical, that's the same, excuse me, if you have, I said this backwards, but all these rules work backwards and forwards. If you have a product of two things underneath one radical, this could be written as the product of two different radicals. They will have the same root index, and that's what that little n is there. It's the second root, which is known as the square root, third root, fourth root, fifth root, sixth root. Whatever type of root you're working with, that little n is known as your index. So again, if you have a product of two things inside a radical, that can be split into the product of two radicals. You just can't change the index when you do that. So if you could split multiplication, of course you could split division, which is exactly what you're seeing here. If you see the quotient of two objects under one radical, you can write that as radical over radical. Again, just don't change the index. That's the root type. Those are pretty straightforward, and those are the ones that we'll use to simplify radicals, quote unquote. Now, rules 3, 4, and 5, they show you some really neat properties of the radicals. This one says, what if you have a radical inside of a radical and they have different indexes? Indices is actually how you'd say that pluralized. You actually get to multiply the indices. So what is the square root of the square root? It's the fourth root. The square root of the third root? It's the sixth root. You get to multiply the indices. Why? Because remember, a radical is an exponent. So if you have a power to a power, you multiply exponents. So you have a root of a root, you multiply the root types. It's the exact same idea. This rule is just showing you that if the root index matches the exponent, they cancel each other. It's like saying, how do you cancel a square root? A square. How do you cancel a cube root? A cube. So on and so forth. The indices match. Well, if the index matches the exponent, they cancel each other. Now, I do want to bring up an important concept here. And that is technically, and I'm saying it like that because we will not be doing that, but technically, if you cancel an even power with an even root, this creates a plus or minus situation, and that would require absolute value bars in certain situations. For us, we are going to assume all variables are positive, so we will not have to do that. Okay? Don't worry, it will not be on my test either. For the test, you will assume all variables positive, so you don't have to worry about when should I be using absolute value bars. So if you go to check in the textbook, you will see there's actually a rule 6 that I cut out. It's not because I don't believe in it, it's because we're just simply not going to use it. It won't be on your test, and we'll just, when things like that come up in the far future in this course, I'll reintroduce the concept. Okay. And then this one I love. Rule 5 is basically saying the order of multiplication does not matter. I know that's not what it looks like, but that's what it says. Because remember, a root type is an exponent. So here what I have is an exponent with an exponent. Well, when we reviewed our exponent rules way back in, was it P1, I think we did that, the very first lesson of the year. When you have a power to a power, you multiply the exponents. And since the order of multiplication doesn't matter, you can switch them. So instead of taking the root of something with an exponent, you can raise a root to the exponent. So this exponent can be in or out of the radical, and it will not matter. It gives you the exact same result. And hopefully that is something that you learned in Algebra 2, and I'm just brushing that knowledge off for you, bringing it back to the front. I hope. Any questions about the rules before we start using them to simplify our radicals, which our book also calls removing factors from radicands. We're going to simplify some radicals. We're okay? So far so good? You guys have seen these things before? Chapter 5 of Algebra 2. Okay. Let's simplify some radicals. Now, I don't know how other Algebra 2 teachers do it, but I basically asked my Algebra 2 students to memorize a certain number of powers. I asked them to memorize a whole bunch of perfect squares and multiples of perfect squares. I asked them to multiply some perfect cubes. I think the first 6 perfect cubes, and it's actually helpful if you know a couple multiples of a couple of them. And as far as the fourth powers are concerned, there was only a couple of them that I asked them to know. Now, if you're not one of those people that knows what your fourth powers are, you could either start building them. Go, okay, let's figure out what 2 to the fourth is. 2 times 2 is 4, times 2 is 8, times 2 is 16. 16 is a perfect fourth power. If you don't have those kinds of things memorized, then what you could do is you could break down this 80. And you could be looking for a clump of 4 objects. Now, the way that you've probably seen this done is by what looks like tree branches to me, just down, factoring the number, so to speak. It works better vertically than it does horizontally. So I'll just scribble in up here where I've got a little bit of space. I don't want you to have to do this. I would prefer that you know some perfect squares, perfect cubes, and perfect fourth powers. But if you don't, and you're going to dig your heels in the sand and go, no, I don't want to learn them, then what you could do is you could say, all right, 80 can be divided by 2, and it'll leave me a 40. 40 could be divided by 2, and it would leave me a 20. 20 can be divided by 2 and give me a 10. And 10 can be divided by 2 and leave me a 5. You see how there are 4 2's here? What that tells us is that 2 to the fourth power goes into 80. Yeah, I don't know, I said that right. I thought I made a mistake. It tells us that 2 to the fourth power goes into 80. 2 to the fourth power is 16. So what I would have done, and my Algebra 2 students would have done, is they would have written the fourth root of 80 as the fourth root of 16 times 5. Splitting 80 into something that is a perfect fourth power and something that's not. And I always take the thing that is the fourth power or is the perfect cube or whatever I was looking for, I'll move it to the front. And the crap that's left over goes in the back. You see this 5 has no perfect fourth powers that go into it except for the number 1, and that never counts because that goes into everything. So it's going to be stuck inside. The way I taught my Algebra 2 students to do it, and I don't care if you do it or not, was circle the stuck stuff. That will tell you in my answer there will be a 5 under that radical still. So if you like that, go for it. If you can do it without that, that's fine too. Fourth root of 16 gets to come out. What is the fourth root of 16? It's 2. That's how we got 16. It's 2 to the fourth power. Oh, he's passing out on me. Go get some water. It'll help. You sure? Okay. Fourth root of 16 is 2. The 2 comes out front, leaving behind a fourth root of 5. And that one's finished. So if you need to break your numbers down, if it says a fourth root, then you're looking for a clump of 4 of those objects. If it says a third root, you're looking for a clump of 3 of those objects. So on and so forth. And you'll notice that when it came out, it was one of those. So, I don't like doing this because what if the numbers are huge? I'd rather you just know some perfect squares, perfect cubes, and perfect fourth powers. But that's up to you. Really, if you know 2 to the fourth and 3 to the fourth, you're in good shape. 2 to the fourth is 16, 3 to the fourth is 81. And that's good enough. And the way I know that 3 to the fourth is 81, because 3 times 3 is 9, 3 times 3 is 9, 9 times 9 is 81. There you go. Okay. Got questions for me on that one, guys? Reducing radicals might have been one of those things that was hard for you in Algebra 2. Maybe it wasn't, maybe it was, I'm not sure. If it is difficult, it might just be a multiplication type thing. Maybe you're just not strong with your multiplications. Maybe you haven't memorized some powers. I'm telling you, memorizing powers, that'll help a lot. Example B, there's no root index written. But that doesn't mean that the root index is 1. The root index is not 2, Luke. What is it? It's 2. Yeah, the root index is 2. See, this is a square root. So it's not written. It's just known. It is a 2. You don't have to put the 2 on there. I'm just doing it for good notes. Is 18 a perfect square? Nope, it is not. But it can be divided by a perfect square. See, the perfect square that goes into 18 an even number of times is 9. Yeah. All right. So I'm going to split that 18. I'm not going to write the root index of 2 again. I just wanted to remind you that it was a 2. And it's going to give me 9 times 2. Now, x to the 5th. X to the 5th, yeah, that's not a perfect square. But remember, I'm just going to creep this thing back up to get to my rules here. What you're dealing with here is a power to technically another power. So this is the 5th power, and this is technically the 1/2 power. What you're doing here, what you're supposed to be trying to do here, is divide your exponents by your root index. But you can't divide 5 by 2, at least not pretty, right? So what do we do? What we do is we split the x to the 5th into something x to the power, a power that can be divided by 2, and the leftovers, x to the 1st. I don't want to write the power of 1, so I'm not going to. If you do whatever, I'm just not going to. And then, like I said, for my Algebra 2 students, I always taught them to identify the stuff that's stuck. That way they know what should be underneath that radical when they're finished. You don't need to circle it? Okay, that's fine. Square root of 9 comes out? 3. Square root of x to the 4th comes out. Now remember, when you are rooting things with exponents, you're dividing the exponent by the root type. So I'm dividing this 4 by this index of 2 that's not written. It gives me x squared. Then I have a square root of whatever's left over, 2x. Like so. There we go. Questions, comments, concerns so far? Okay. Don't be afraid to talk to me. Now this next one. The first thing that jumps out at people is that they see that negative sign in the radical. They go, oh, impossible, imaginary. Go, no, 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 no. What type of root is it? It's a cube root. It's an odd root type. And you can take odd roots of negative numbers all day long. No worries. The result is negative. And that's because if you multiply three negative numbers, you get a negative number. So yeah, odd roots of negatives, 100% allowed. Now, is 24, don't worry, I know it's negative 24. Is 24 a perfect cube? No. But it can be divided by a perfect cube. It is divisible by 8. 8 is 2 to the 3rd. So what we'll do is we will write it as the cube root of, and the strong suggestion is bring the negative sign with the perfect cube. Negative 8 times 3. Yeah, 8 is 2 times 2 times 2, so 2 to the 3rd. And like I said, we are trying to divide our exponents of our variables by our root type. If it divides pretty, then you don't need to split that variable apart into multiple pieces. However, if it does not divide pretty, like you just saw here, then you have to split it. And no, 4 does not divide by 3 pretty. So we split the x into something that has an exponent that is divisible by 3, happens to be 3, and however many of them are left over. Again, x to the 1st, I'm not going to write the 1. 6 does divide by 3 pretty, so there is absolutely no reason to split my y's. I'll go through and identify the things that will be stuck under the radical in my final answer. There we go. Oops. Forgot my root index of 3. Sorry about that, guys. Root index of 3. And here we go. Anything that doesn't have a circle on it, I could take the cube root of that. Cube root of 8 we said was 2, so the cube root of negative 8 is negative 2. Dividing this exponent by this root type gives us a 1, so I have an x on the outside. Dividing this exponent by our root type, which is a 3, it gives me 6 divided by 3, which is 2. So y squared comes out. And the things I circled are stuck inside this cube root. So there is us reducing radicals with and without variable expressions. We're not going to worry about imaginaries yet. So even root types of negative numbers, not today, and it should not be in the homework. I did everything in my power. I'm pretty sure I avoided them completely because I'm going to be talking about imaginaries, complex numbers, starting tomorrow. But do you have any questions about me? Excuse me. Do you have any questions for me about reducing radicals, barring imaginaries? No? Yes, ma'am. Well, so the reason why we're not, yeah, because it's cubed. So the only time you do division is on the exponents. Yeah, the only perfect cube that goes into 3 is 1, but 1 doesn't count because it goes into everything, right? But yeah, that's why, because it's a coefficient, not a exponent. That's why. Okay, so something that I honestly really can't stand, but I do have to teach you because Ms. Klein is a stickler for it for some reason. I don't know why. Yes, that's right. That's going to be on YouTube. Is rationalizing denominators. Be real with you, in college, most professors, sorry, I just got this mouth. They don't care if you rationalize your denominators. In fact, a lot of them will tell you don't because it makes grading harder. But let's say we came to the agreement that I would teach it. I don't want to, but here we go. Technically, you're never supposed to leave a radical in the bottom of a fraction. Why? I don't know. But that's just what they say. You shouldn't have a radical in the bottom of a fraction. So what do? Well, if we have a radical in the bottom fraction, we rationalize the denominator. Now, most of you would have learned this already, but maybe you didn't learn about how to handle it when there's other root indices. So what do? First, using rule number 2 from the box up above, the fraction inside the radical can be split into a radical over a radical. Now this thing's root index down here is a 2. I know it's not written, but it's a 2. And if you look at rule 4 in that box up there, it says exponents that match the root indices will cancel each other out, leaving just the object that was inside the radical. It's called the radicand. So our job then is to get the exponent on this 3 to match the root index. This root index is a 2. So the only way that I could get this exponent on this 3 to match this root index is to get 3 squared down here. So we will multiply by root 3 on the bottom, because that will give us root 3 squared technically. But you can't just multiply a number to the top of a fraction. You have to to the bottom. You have to multiply it to the top and the bottom to make sure that technically you're multiplying by 1. So multiplying by 1 doesn't change anything mathematically. It'll manipulate the way it looks, but it hasn't changed its value. On top, this will give us the square root of 6. And on the bottom, it will give us the square root of, well, 9. And to be honest with you, I'm going to write the square root as 3 squared. Because I'm really trying to drive home the fact that when the index matches the exponent, they cancel each other out. That will leave me with my answer of root 6 divided by 3. And I don't know why I was writing so crooked. And I believe I said to you guys a few days ago, inside things cannot play around with outside things. This 3 cannot reduce this 6 because this 3 is outside a radical, this 6 is inside a radical. But the square root of 6 divided by 3 is the exact same thing as the square root of 2/3. They're mathematically identical. A lot of you probably have already seen that. But do we know how to rationalize the denominator when the index is not a 2? See, this index is a 4. We go, okay, well, remember, if you're trying to cancel a fourth root, you need a fourth power. But you're not allowed to raise the top and the bottom of a fraction to exponents. That changes the value. You can't do that. So what we need that thing down there to say x to the fourth. Right now it says x to the first. I hope it's obvious that you need 3 more x's underneath that radical. Because if you had 3 more of them, you'd have 4 x's, and then the exponent would match the index. So what I'll do is I'll multiply by the fourth root of x to the third. That will give me the other 3 x's that I needed. And if I do it to the bottom, I have to do it to the top. That will give us the fourth root of x to the third on the top of the fraction. Something just happened in my brain, sorry. Fourth root of x to the third. And on the bottom, I'm going to have the fourth root of x to the fourth. Again, really trying to drive home the fact that when the root index matches the exponent, those things cancel each other out. This and this are 100% identical. Now, I know it's an opinion, but which one of these two answers looks like it's better to look at? The one you started with or what you ended with? Yeah, I mean, if you were a professor trying to grade somebody's work, wouldn't you rather see that? I mean, that's really concise and compact. This is ugly. But, you know, I know that's an opinion, but that's why most upper-level mathematicians, especially in the college level, don't want you to rationalize your denominators, because it takes things that look elegant and makes them look like Frankenstein. But whatever. Ms. Klein and I have to agree on what we teach, because we teach the exact same stuff. Alrighty. So question C here is going to combine the two concepts from A and B. So we do have a fraction inside our radical. So what I'm going to do is I'm going to write this as the fifth root of x squared over the fifth root of y to the third. That fifth root on the top of the fraction, no big deal. That's not a problem. No. The problem is we have a radical on the bottom of the fraction. That's the no-no. The fifth root's job is to cancel a fifth power. So if this exponent on this y was a 5, that fifth root could do its job. There's 3 of them now. That means I need 2 more of them. So multiply the top and the bottom by the fifth root of y squared. On the bottom, I will now have the fifth root of y to the fifth. That makes us happy. And on the top, since they have the exact same root index, I can use rule number 1 in reverse, that's in that box at the top of the page. Because they have a matching index, I can put both the x squared and the y squared inside that radical. Fifth root of x squared, y squared. Over, and on the bottom, like I said, fifth root of y to the fifth. Hopefully it's becoming insanely obvious. When the indices match the exponents, they cancel each other out. And there it is. Sir?
Where'd you get the y squared?
So the reason why we use y squared is because we needed this fifth root to be able to do its job. It could only do its job on a y to the fifth. So if I already had 3 of them, I needed 2 more. That's where. So basically, you're asking yourself, how many do I have? How many did I need? Let's get how many. Let's get the rest on there. So like for this one, technically I had a 1, but I needed 4. So I had to grab 3 more of them and tack them onto the top and bottom. And that can be done with numbers as well. So if it says, and I don't think it's in the homework, but it said like 1 over the third root of 9. You know, if I'm saying it, I might as well write it. Impromptu extra example. What you don't want to do is go, oh, that's a single 9, so I need 2 more of them. That's too much work. You don't want to do that. Instead, what you'd like to do is realize that 9 is 3 squared. So really all you need is this one more 3 on the top and bottom. Because then you'd have 3 to the third inside your third root. That's a lot of 3's. I'm sorry about that. It's just the way it happened. Still a lot of 3's, but I want to make sure the numbers are small. So could I have multiplied the top and bottom by the third root of 9 squared, which is 81? You sure could. But there's not a lot of people that know really, really quick that 9 to the third power is 729. You know, so I'd rather just keep the number small where I can. But that's how you would do that kind of thing. I don't think that happened in the homework. I just wanted to make sure that you saw it in case it ever does happen. So I've already mentioned it, said it a few times actually, that radicals are exponents. And I already kind of hinted at it when I said that the square root was the 1/2 power. So this box right here just reminds us, how do we turn a radical into an exponent? That's what this box is all about. Basically, the root type is the bottom of a fraction exponent, and vice versa. If you have a fraction exponent, the bottom of it, the denominator, is your root type. So if you have a fractional exponent, let's just say it says x to the, I don't know, 4/7. I'm just making up ugly numbers here. Then this could be written as x to the 1/7 raised to the 4th. Or it could be written as x to the 4th to the 1/7, because multiplication doesn't care about order. And in radical form, this would be the 7th root, and this would be the 7th root of x, quantity to the 4th. See if I could squeeze it in down here. 7th root of x raised to the 4th. And this would be the 7th root of x to the 4th. There's 1, 2, 3, 4, 5 different ways of representing the exact same expression, just by changing the order of what you're doing first, the exponents or the radicals, or just writing it as a fractional exponent. So I need you to be able to do all 5 of those things. I need you to be able to turn fraction exponents into radicals in both orders. See how that exponent, that 4, moved in and out to be the same thing? And I need you to be able to say that you could either have 1 over denominator raised to numerator, or x to the numerator raised to the 1 over denominator. I just need you to be able to split your fractions apart like that. All 4 of those are the exact same thing. They're all x to the 4/7. But that's what that table there is telling us. I think it's easier to see with numbers. And again, and if you still happen to have your Algebra 2 book, first of all, shame if you take it back. Shame on you. But if you happen to have your Algebra 2 notes still, you'd be looking in Chapter 5 for this kind of stuff, if you want to do extra review. Alrighty, so if we flip it over to the back, we'll get to do some examples with this stuff. Flip them. Let us simplify some exponential expressions. Woo! Look at that. Alright, well, we've got some options. You know, there's a couple different ways that we could approach this. I think that I want to tackle this with fractions, not exponents, not radicals. So fractional exponents instead of radicals, because I think that fractions are easier to work with than radicals. And so for this first set of parentheses, I'm going to remind you that when a set of parentheses have an exponent, as long as everything inside is separated by multiplication, which x squared and y to the ninth are, you apply this 1/3 power to both of these objects. And remember, power to a power says multiply. So what we're going to have here is x to the 2 times 1/3 times y to the 9 times 1/3, which will just reduce to 3. Yep. I am still going to keep this in parentheses, though, and here I have an x y squared. I left us lots of space so we can show all the steps. If you can get there faster with less steps, that's fine. It's 100% okay with me. Cool. All this is multiplication. So back to our exponent rules. Yes, sir?
Is the first set of parentheses being raised to the 1/3?
Yes.
Oh, okay.
Yes. The first set of parentheses is being raised to the 1/3 power, which is why I applied it and multiplied my exponents, because it was power to a power technically. Now, all the way back to p.1, when you multiply two numbers with the same base, you add their exponents. This does have an exponent. It's a 1. So what we have here is x to the 1 2/3 which is incredibly weird, times y to the 5th. And that's exactly what we're going to do, because mixed numbers are awful. Mixed numbers are only good for changing the oil and baking cakes. If you're not a chef or a mechanic, then use improper fractions. Improper fractions are the way to go. So we will convert this 1 2/3 to a 5/3. And just in case you're not sure how to convert mixed numbers into improper fractions, I will remind you off to the side here in a little, I'll make a bubble around it. The way we do this, in case you haven't been taught, I mean, I don't know where everybody comes from, is like this. You multiply, so you multiply down, and then you add up. So 1 times 3 is 3, plus 2 is 5. There you go, 5/3. That's how you would get the 5/3. So that's how you're going to convert that to a mixed number, or from a mixed number, excuse me. Or you could have found the least common denominator between 2/3 and 1. So you could have said this 1 was actually 3/3. And you have 2/3 plus 3/3, 5/3. Either way, you pick one. As long as you can get to the right answer, I'm happy. All right. Question B. Would you believe in the textbook there's no work shown? It goes straight to the answer? I'm not going to do that. We're going to show some work here. Okay? Again, you guys, you show some work in your homework just to show me that you didn't just copy it from somewhere. Oh, also, in your homework, can you guys, instead of writing the section that it's coming from, I know a lot of you are doing that, like P.3 and P.4, can you please just write the homework number on it for me? So like tonight's is homework number 5, if you would please. That makes life a lot easier for me to grade. Getting into the computer is a lot faster. Please, please, please. Anywho, what do we got going on? Well, we have multiply straight across the top and straight across the bottom. That's how you multiply fractions, straight across. 3 times 2 is 6. X to the, all right, well, since I'm technically multiplying two numbers of the same base here, I'm just adding their exponents. 2/3 and -1/2. That's the same thing as saying 2/3 minus 1/2. And on the bottom, y to the, again, multiplying two numbers of the same base, you add their exponents. 1/2 plus 2/5. We need least common denominators. The least common denominator between a 3 and a 2 is a 6. Yeah, so we're going to multiply the top and bottom of this one by 3. Top and bottom of this one by 2. X to the 4 over 6 minus 3 over 6. And down here, least common denominator between a 10, said the answer, between a 2 and a 5 is a 10. So multiply by 2 on the top and bottom, multiply by 5 on the top and bottom. Y to the 5 tenths, excuse me, plus 4 tenths. Giving us 6x to the 1/6 over y to the 9 tenths. Boom. Hardest part about this should be adding and subtracting fractions. I can't, well, I could write this in radical form if I wanted to. Or I could just leave it as is. Depends on what the directions say to do.
Well, can't you not have a radical?
Oh, you mean rationalize the denominator?
Yeah.
Yeah, we could. That's the thing. Like, that's why I hate rationalizing denominators, because when should you leave it like this? When should you rationalize, right? Technically, you're not wrong. Technically, this is not allowed because this is a 10th root in the bottom of this fraction. So I'd have to multiply by the 10th root of y on the top and bottom, or a y to the 1/10 on the top and bottom, and just yuck. You know what? I'm just going to leave it like that. Honestly, something like that never shows up on any of my tests because I don't believe in it. I just think it's a waste of time to do it. You're not wrong, but basically the only time you're going to have to rationalize for me and for Miss Klein, because she wanted it, is like, oh, we're not going to leave a square root of 2 in the bottom of that. So we'll multiply by root 2 on the top and bottom. We won't ever do it with variable expressions. Either one of us, we never do that. We're just going to leave it like that and say, well, it's a fraction, it's not a radical. Let's leave it like that. Lastly, let's combine some rules here. Here I have, well, that's really tiny, the third root of x to the 5th over the square root of x. And we're going to combine some rules. I would like to write this as using a single radical or a single rational exponent. We're going to do both. Okay? So writing this larger, I have the third root of x to the 5th over the square root of x. The root index is not written, but that root index is a 2. And the power on that x is not written, but it's a 1. Working with the radicals makes this very difficult in my mind. So I think the first thing you should do is convert it to exponents. X to the, remember, the index is the numerator of the fractional exponent, the rational exponent. So this is x to the 5/3 over x to the square root means 1/2 power, like that. Now it should be much easier. Back to p.1. What do we do when we divide two numbers with the same base? What do we do with the exponents? Yeah, you subtract. And it's supposed to be top minus bottom, but it's even quicker to go, what's bigger, 5/3 or 1/2? 5/3. What that tells us is that our x's will remain on the top of the fraction. So we're not going to have to, if you do it this way, you will never have to get negative exponents. If you decide where they're going to be, top or bottom, then you just put them down there and you do the subtraction. But this is going to give us x to the 5/3 minus 1/2. And again, we need a common denominator. The common denominator between a 3 and a 2 is 6. We've already seen that happen. So multiply the top and the bottom of this one by 3. Top and the bottom of this one by 2. X to the 10/6 minus 3/6, which is x to the 7/6. That is the single rational exponent portion of the answer. And then the single radical portion of the question is converting this fractional exponent back into a radical, remembering that the numerator is the root type. Denominator is the root type. The numerator is an exponent that can either be written inside the radical or outside the radical. It doesn't matter which one you choose. They say the same thing. I'm going to go with inside, only because it's smaller than the, only because it's less to write, I think. So I don't have to write parentheses and stuff like that. You know what? I'll write them both because it's good notes this way. All three of these things say exactly the same thing. That and those two. Yes, sir?
Does it matter which way you write it on the test?
You would just have to follow the directions, because the directions will be very clear about what format it needs to be in. And since it's either going to be multiple choice, multiple select, or fill in the blank, it'll be pretty obvious which one you have to choose.
Yeah.
And that's it. You guys have questions for me on it? Be happy to answer them. No? Yes, sir?
So why do we? Oh wait, no.
Are you sure?
Yeah, I was wondering why you wrote the 2 there, but yeah.
Oh, this one?
Yeah.
That's just to remind everybody,
Yeah.
because some people think it's a 1. It's like, no, if it's not written, it's actually a 2. That's the only reason why. Cool.